Let's look at the simple facts about global energy balance. Okay, so sun is emitting at a mean average temperature of 6,000 Kelvin. Temperatures are much higher as you go inside, but the Earth is radiating, on the other hand, at 255 Kelvin. Okay, so 6,000 Kelvin versus 255 Kelvin. Then the question is, when the energy balance happens, Earth is receiving almost all its energy from the sun, and it's emitting at a different wavelength. So how is the energy balance happening? Obviously, the energy received is going to be spread over the area of the Earth, but how does the balance happen? And what are the things we want to look for? The properties of other planets will help us better understand why Earth is special, why Earth's energy balance is different than our neighbors. For example, if you look at Venus, its radius, its energy flux, which is 2632 watts per meter squared, as opposed to Earth's surface flux. This is the average energy you receive at the top of the atmosphere per unit area, which is easily measured by satellites, for example. So why is this different? Because the Earth's distance is further out from the Sun than Venus. And remember, the flux from the Sun drops off as 1 over r squared, where r is the distance from the Sun. So there is a quadratic, inverse quadratic relation. So Mars, for example, drops off to 589, and Jupiter drops off to 51. We will learn a concept called albedo, alpha, and Venus has a very high mean albedo because of its gases in the atmosphere. It depends totally on the temperature of the gases that are emitting the radiation in terms of energy balance, but the albedo itself is just the reflectivity to the sun's radiation. Sun's radiation is coming in the short wavelength. Anything that reflects it directly without absorbing or allowing it to evaporate, melt the glaciers, etc. on Earth, is going to be lost back to space. So albedo is the reflectivity, right? So Earth has an average of 0.3, Mars is 0.24, and Jupiter is much higher at 0.51 than Mars and Earth. The key question we want to answer is the emission temperatures and the surface temperatures. Because we live on the surface, we're going to be interested in the surface temperature. So emission temperature is what is balancing the incoming energy with the outgoing energy. We'll see exactly how it works. So Earth is emitting at 255, whereas Venus is emitting at 227 Kelvin. Mars is at 211, Jupiter at 103. But if you look at the surface temperatures, Venus is at a scalding 760 Kelvin. Earth is at a balmy 288 Kelvin, and Mars is at 230, Jupiter at 134. There are differences in the rotation rates, or time it takes to make one rotation around its own axis. Earth is defined as 1, whereas Venus is spinning much more slowly, 243 Earth days for one rotation, and so on. Mars is very close to us. So considering these relatively small differences between the solar flux at the top of the atmosphere for Venus, Earth, and Mars, why are the temperatures so wildly different? Why is Mars at minus 50 degrees centigrade and Earth is at 15 degrees centigrade and Venus is at 460 or so degrees centigrade? That's what we have to understand. So let's look at the spectrum of energy. So here is the energy emitted, and here is the wavelength. So this is for the sun. So sun has very long, short wavelengths at gamma rays, X-rays, and so on, coming into energetic UV light. Obviously, the energy drops off towards the very short wavelengths and towards the very long wavelengths. And in the visible band, Sun emits most energy, so Earth is receiving most of its energy in the visible. We'll see that the UV gets absorbed in the stratosphere. There is a rule called Wien's displacement law, which allows us to estimate the surface temperature based on the measured frequency or wavelength of the energy that's being emitted, which turns out to be in the middle of the visible. So here is the relation between wavelength and energy emitted. So the hotter you get, the shorter the wavelength at which a body emits energy, right? So sun is somewhere here. If you have other stars that are much warmer, then their energy would be coming in at much shorter wavelengths, and if the temperature of emission is much lower, then you get a much flatter wavelength distribution. Okay, that's important because who intercepts how much energy depends on what happens to that energy and who can absorb or emit or reflect that energy, right? What are the albedos of different surfaces? Ocean, it depends on the angle of incidence of the light. The best example is to think about flying in an aircraft, if you have done that, and if you look out the window, if it's daytime, the ocean might appear very bright if sun is shining at an angle, but if sun is more overhead, then the ocean might appear very dark. So almost all of the energy may be absorbed by the ocean when the sun is overhead, whereas a lot of the energy might get reflected if there is a high angle of incidence to the surface. Forests are fairly dark. Cities, grass, soil, grassland, deserts are fairly bright. We'll see that in the next podcast. Ice is very bright, 20 to 70% albedo, which means up to 70% of the solar energy may be reflected back to space. This is obviously important because ice forms when it's cold, and if it loses a lot of the energy, it has the potential to make it even colder by losing most of the energy back to space. Clouds depends. There are bright clouds and there are dark clouds. Snow is also like ice, highly reflective, and it depends on whether the snow is old and has melted and has a lot of water in it, or it's still fresh and is mostly in the form to reflect the sunlight. So that's kind of the brief introduction to the energy coming in and the wavelengths that matter for how the energy is being sent back to space. So the balance is basically going to be between the incoming energy of the sun, which is mostly in the short wave coming to the top of the atmosphere, and the emission by the planet, which is in the long wavelength. So we'll look at the wavelengths and we'll do the energy balance in detail.